Camera, you mean the camera thing? Okay. So let's see, this should be okay, high quality camera, so maybe it can do the trick.
Here you're just going for changing the light. So we have to wait. Looks okay.
So it looks okay.
Yeah.
Yeah, it looks very good. I think the one thing that will be unclear if I'm writing something to this blackboard. But other than that, it should be okay. Looks okay.
Are you gonna write something on black?
I could. This is usually my teaching style. If I would do a live lecture, I would like to use these slides, but also I'd like to clear things by using the drawings here in the blackboard. That's my style. But anyway, so maybe there's not much things to draw today. So, last lecture. I mentioned one of the lectures in this period that there is this extra possible lecture right after Labor Day. And I don't think we need it. I don't think so. We'll see. I have a 60-something slide, so depending how fast I'm doing today. And it seems to range a lot from one week to another. Some weeks I realize that I'm very, very slow, whereas in other weeks I'm doing better. That's unpredictable. So, so what happens today is that I want to discuss something about how to describe large deformation, where that is needed. And this is something that is heavily related to research we're doing in LUT University. Some, I think 5 years back, each of the professors got a letter from the student union, and the student union were unpleased about the fact that many of the lectures are not touching the research we're doing in LUT. And they actually wanted to have students to get more involved with the research we do. And that's of course a beautiful idea, but very difficult to do in practice. And what it is difficult to do in practice, that is related to how much you need to get involved and how much you need to be committed to be able to do the research. So it's not like something that is an additional assignment, like weekly assignment. That's not really what we do as a research assignment. Let me tell you a little bit like why it's not the same thing. Because single paper, the one paper that is published in a journal typically takes a 1 year time to prepare the manuscript. So it's not yet accepted, but just the putting together all the material, all the theory, all numerical examples or practical experiments, it takes a year, roughly a year. Now, if I would give you an assignment, and this, by the way, is for average doctoral student. An average doctoral student, I could say that is a second year doctoral student. First year doctoral student needs more than a year. Master level student needs 3 years to put that together. So if I would give you an assignment that here's a big great idea, make me a paper out of that, it will take you the entire master degree. And that's not fair to you, because in a master degree, it's not so much about the research, but more about getting the knowledge from different subject matters. So that's why it's a little bit unrealistic. Of course, then the answer is that, okay, you can be part of the team. Yes, you can be a part of the team, but the team members should be more or less equal level of knowledge. So it not make much of a sense if there is a team member that is dragging his or her feet. So that's not a good idea. Okay, so anyway, so that was a request from the student union offer. Student union, I think it's a good idea. So what I decided to do then is that I'm going to give one lecture or half a lecture. Well, 1/3 of the lecture, which shows a little bit what is then we do then as a one topic of the research. You already learned about the biomechanics. That's something we do. We don't do the bicycle dynamics like was explained by Professor Arjen Schwab from Delft. That's a little bit off topic for us. We don't do that much about the vehicle dynamics, except we do railroad dynamics. And by the way, now I realize that if you would like to learn about railroad dynamics, there is a topic available in that area too. So it's up to you. So if you would like to learn, I'm saying that this one extra lecture that I mentioned to you earlier, I can deliver this one extra lecture. I mean, I cannot deliver it, but one of my postdoc can do it, and it will be related to railroad dynamics. Would you like to learn railroad dynamics? Because the railroad dynamics is like weird thing. It's a miracle that there are trains and trams. So, and why it is a miracle, that you will learn if you're gonna participate that lecture. So one lecture about the railroad dynamics. I just remember that there was this one postdoc that would like to deliver this extra lecture. So I think that would be a good idea. Railroad dynamics.
Is it gonna be next week?
No, next week Monday is official holiday. So this week Friday and next week Monday those 2 days are holidays. I don't know how is the Thursday in the university. Some of the schools, at least in this region, are off already on Thursday. Some are not. I don't know how is the situation in university. I don't know if it is a holiday or not. But the Friday for sure is a holiday. That's a religious holiday as it is a Monday. Okay. So don't come to university. I mean, you can of course come to university on Friday, but the cafeteria will be closed at that day. Okay. So then the thing that if I have a time, I would like to spend some time to explain you a few matters related to your master thesis work. This is the kind of like similar kind of information that this career counseling, except that this is very much into the topic that is going to be very much valid for each of you soon. Maybe it's already valid to you. So just that, what are the things that is good to take into account regarding the master thesis? What about these urban myths about financial compensation? What that means, how many of you will get that financial compensation? Is it reasonable to ask to get the financial compensation? This kind of stuff is that lecture. And then the really like how is that you should put together a thesis work? What are the chapters you should have in your thesis? This kind of stuff. Okay, so that's if we have a time today. If not, then I think that this is not going to be the last lecture, but then there's going to be one extra supplementary lecture about railroad dynamics and master thesis work. So that's not going to be next week Monday, but let me think. What is a Monday after that? What day is that? It have to be like 28 or 25, 25th. Okay, all right. Okay, so here is again the summary. How is the things? You know, we discussed a week ago about the stress analysis, contact modeling, and now we're gonna look at something that is a large deformation. That the large deformation is something that, for level of expertise, is the one that is utmost right position. It really needs a lot of knowledge to be able to use it, and it's not so well applied. It needed in some cases, but generally speaking, not so much needed. Why is that? That's the way that I will get started. Okay, large deformation. So I'm going to discuss about one single method. And this one single method, because this is a method that is heavily being developed here in LUT University. There are other teams worldwide that is also into this formulation, but here there's been quite a bit of projects, quite a bit of effort to develop the one formulation, new formulation for multi-body system dynamics. And that's the one that is called the absolute nodal coordinate formulation. What is this method? That I will shortly explain to you. And again, this is because it's give a highlight about the one topic we're doing in the research. And this one topic is related to flexible multi-body dynamics. Okay, so there's a little bit of element technology, because most of the publications produced so far are somehow related to this element technology. Element technology means like finite element method consists of elements. How is it you can create those elements? This is what that is about. So, and then a little bit about applications. Okay, now, large deformation case. You know that multi-body system dynamics was started in rigid bodies. So there was this need to analyze dynamics of system that consist of multiple bodies, and there was a very inherent assumption which was related to flexibility of the bodies. So initially, it was assumed that there is no mechanical deformation in the bodies. And this is what we learned in the very beginning. So it means that whatever force is applied to your bodies or system, there is no mechanical deformation. And you know that this is alright assumption in many of the cases. Whereas some of the cases, it's not capable to produce acceptable solutions. And acceptable solutions because mechanical deformation is a part of the dynamic response. And if you ignore that, you can get the solutions that is not according to reality. So then some 30 years ago, there was this need to make more accurate models. And that time, this floating frame reference formulation was developed. There were prior formulations like this linear theory of elastodynamics, method based on land masses. But then this method that is dominating at the moment came into play, and that's the floating frame reference formulation. And again, the reason was obvious, to make more accurate models, to make more realistic models. But then it became clear that even this floating frame reference formulation is a little bit limited. It is limited because remember what we're doing in a floating frame reference formulation, we're using these modes. We're using these modes, and because we're using these modes, deformation is typically assumed to be small. And it's small because the strain displacement relationship is linear. And that's because, again, we're using these modes. Okay, and then there are cases that you would like to analyze large deformation. There are like cables where this assumption is not valid. There are belts, ropes, clothes, many other applications where this assumption is nowhere near to be correct. And there was quite a bit of effort to try to find how is it we can model those kind of special cases as well. And that's when the absolute Norakone formulation was introduced. And it's quite typical that the one single model consists of many levels of bodies, rigid bodies, then bodies that are capable to deform a little bit, floating frame reference formulation, and the bodies that are capable to deform a lot. And that's the absolute Norakone formulation. Here, it could be the case that these belts are based on the absolute Norakone formulation. Pulleys would be rigid bodies. There is nothing here that is described by the floating frame reference formulation, but you got an idea. So those are the typical models. So how is it you can describe this large deformation then? How it goes? And that's what I'm going to explain you in next 20 minutes. Let's see. That's a challenge. If I can do that. Well, maybe not 20 minutes, but something reasonable. Something reasonable. Okay, this is where it's getting started. And this is already heavy stuff. You know, this method, this floating frame reference formulation, the absolute Norakone formulation, this is a special method in a sense that it uses the very simple kinematics, super simple kinematics. This is so simple kinematics that none of the other methods we are described earlier are capable to do it. So what is this simple kinematics then? The simple kinematics is the one that is shown here. You know, every single particle with respect to global coordinate system is described by linear combination of shape function matrix and the vector of nodal coordinates. It's simple like that. And this is, remember, we used in finite element method, we used this kind of like the same description. It was n at the time that we said. So n was the one that was described. And I think this was, let me think how it was. It wasn't E, we used something else notation, which I don't remember at the moment. I think that it was called like U something. This was a nodal coordinate, this was a shape function matrix. The one that is describing the possible deformation within the element. Remember, this is the one that you introduce this unit displacement to here, and you're gonna get like this kind of deformation, and then you're gonna introduce this rotation here, and you're gonna get like this kind of deformation. This was the thing we described. So those are the shape functions. Now the shape functions are described by nodal degrees of freedom, which are these, are the way that the element can deform. This is what we used in the finite element method in the beginning. But the finite element method was not able to deal with the orientation of the elements. So they will have to use this orientation matrix, and all that have to be put in this floating frame reference formulation to be able to use that in a multi-body system dynamics. Remember, eventually everything was have to describe with respect to this floating frame of reference, and that with respect to global coordinate system was this long story like this. This is this coordinate system, and then U0 plus UF. That was the whole equation. And now what I'm saying here, that let's just simplify. But let's simplify it in a way that let's use directly this one here. That's it. So it obviously needs a trick that have to be done for this particular matrix. And have to be, maybe we need to play with this vector of nodal coordinates as well. But the kinematics is this simple. Couldn't be more simple than this. So a simple method. Okay, so what is that we're doing then? How is that we can make this trick? How is that we can make this shape function matrix such that each of these complications disappears? Well, it disappears. Now this, by the way, was found by a Luck. And it was found by, I have this history in my postdoc period I spent in Chicago, in University of Illinois at Chicago, UIC. And in that university, there is a Professor Ahmed Shabana. So if you make a list about who is the most known professors in the field of multi-body system dynamics, first comes Ahmed Shabana, then comes nothing, and then after a little while, rest. So he's like clearly the most well-known researcher in this field. So he found this method by an accident. That's what he explained. And the accident happened because he tried to explain floating frame reference formulation to finite element community. And he made a simple example how it goes, and he ended up to have a method which then was called the absolute nodal coordinate formulation. So it was invented 1999, something like that, very close to 2000. And I started there 2000. So I was one of the first ones in this formulation. And it's been with us since that. Not so much effort anymore, but still it's been with us. And that comes, now when you look at the papers that are related to this formulation, there are a lot of familiar faces. Many of the teachers that are currently active here in LUT, they make their doctoral dissertation from this topic. Okay, back to this trick. So what is the trick we can do for this guy to make the kinematics to be simpler? Well, we can use something that is called vectorization. I don't know if it is really a correct name or not, but the vectorization is a simple procedure. And it goes such the way that, this is the beam element we look, when was it? In the beginning of the course. Remember we look at the beam element such that the beam element was consisting of a total of 4 degrees of freedom, 2 degrees of freedom for each of the nodal locations. So there was a displacement in the y direction in this node here, if you can see this one here. There was a rotation associated at this point here, and the same nodal degrees of freedom for this other end. So what we then do, So what we then doing is that instead of using this kind of simple scalar quantities describing the point of a nodal location, we can use a vector. So instead of using y, which is a displacement in this transverse direction, we can use r, which says simply that this point here with respect to global coordinate system, R. That's our nodal degrees of freedom, meaning that this point here can travel here and here. That's it. So it's very close to this original finite element method. Okay? And then the rotation is this R, like we did here, Y, and the rotation of degrees of freedom was a partial differentiation of Y with respect to X. Now the similar case, we're going to take the partial R, partial X. This is a vector. This R is a vector, meaning that this slope here consists of two components as well. And the same for the second node. Now, because of these dimensions are different, these shape functions have to be multiplied by an identity matrix, which is 2 by 2 identity matrix. And this is it. This is the kinematics. Now, this kinematics can describe large translation, large rotation, everything. Everything works. So it's very, very simple. So that's about it. There is some difficulties because, when you're parameterizing your element as a line, then you cannot take this transverse shear into account. You may not know what the transverse shear deformation is, but simply it means that if you take a, let me take this off. But do you know what the transverse shear deformation is? No, you don't. Have you ever heard of it? It's used in a structural strength analysis very heavily. But it's something that if you want to build a bridge, transverse shear deformation. So if you want to build a bridge, such the way that this is the bridge. Okay, and you have 3 beams in your use. Let's say three pieces of wood. So you can put it like this. And this is the third one. Okay, this is your bridge. Okay, so how it's gonna behave if you're gonna go and sit or you're gonna stand here in the middle? How is this wood material? How is they gonna behave? Well, they're gonna behave in a way that they're gonna bend. Yeah, they're gonna bend like this. But because the bridge is made in such a way that these layers are not attached together, the layers are moving with respect to each other. Okay, so they are moving in with respect to each other, and because they're moving with respect to each other, the strength of this bridge is not so great. So it's deformed like crazy when you're standing it. You can make it more rigid by building or attaching these beams together. And this is preventing them to slide with respect to each other. So now the stiffness is going to be much higher. And this is now something that demonstrates, now this is this shear deformation that they're moving with respect to each other. It is prevented by these bolts here. And that's what the shear deformation means. So it's like the possibility or the kind of tendency that the cross section is not perpendicular with respect to midline. So if you have a midline here, it's a perpendicular mean like this. But when there is a shear deformation, it's not exactly perpendicular, but something else. So that's for your information. Now, finite element models, elements, almost all of them, except the ones that are really like historical ones, are capable to take this transverse shear deformation into account. But now in the absolute Norakone formulation, we have this line parametricization. And when you have the line, the only way you can see the cross section from the line is that you have to make an assumption that the cross section is perpendicular with the midline. There is no other solution. There is no way to do it. But if we want to take this into account, so if we want to take into account that the cross section is not perpendicular but like this, how is it we can do that? Well, we can take that into account by using another set of vector. And this another set of vector is going to be the the trick that was used here in the absolute Donat-Conner formulas. This one here, this angle and the partial differentiation, that's the case when you have these transverse shear deformation. So when the transverse shear deformation is important in the practical cases, when the structure is thick. So you don't need to care about it if you have a thin structures. But thick structures, you need to take care of that. Okay, how that was accounted in the absolute Donat-Conner formulation? By adding more slopes, adding more components. So now if initially there was this R that described the motion to x and y direction, then there was a slope, partial R, partial x. This was this orientation of the midline. Then there's one more slope. So I'm going to take this R one more time. I'm going to differentiate that with respect to y. I'm going to get the slopes. If this is R, there's going to be slope this direction, and they're all independent. That's how it goes. Okay. All right, so let's move then. And then, remember I mentioned this story about, how I spent, how many months I say? 3 months in my life to get this shape function matrix for a single special element. Here it is. I still when I see this, I'm like scared, like, oh my God. This was such a miserable experiment. And, this was the element that I mentioned. So this is a plate element, extension from the beam to plates. And to find this configuration, this one here, oh my God, it was a major effort. It looked like a simple thing, but this is not what is called is a consistent shape function. So it was not selected from the Pascal's triangle in a way that it was like everything in a row. Not at all. So it was like some of them were selected here, there were some here, some here, some here, some here, and some here. Finding the proper combination, that was a major headache. Major headache. Sometimes that's what the research is. So it needs quite a bit of luck to make it happen. Sometimes things happen as an accident. I wasn't sure if this was an accident or what, but that was an example. Now, what these slopes are standing for then. So what they're describing. Well, if I think about this beam element here, and if I look at this in a three-dimensional space, this consists of 3 components. This is 3 components. This is 3 components. 9 together. What the heck? 9. Isn't it so that the one point, this one here, it can have a translational degrees of freedom, a rotational degrees of freedom. That's going to be 6. 6. But here is 9. So what are the rest 3? Rest of the 3 describe the deformation of the cross section. They're describing the distortion of the cross section like this. And also, the cross section can shrink and get bigger. And the same for plate elements. So the fiber deformation, fiber is the one that goes off from the midline, from the plates. That's what it's called, the fiber deformation. And in the cases where there's a higher order elements, if you get the higher order derivatives, they describe even more complex shapes of the cross section. Okay, and that's what they were. Okay, this I'm gonna skip. This was the way that the elastic forces can be described. All right, but then there is a story that I want to share with you. So, or did I mention this story about Jussi Sopanen to you already? So I mentioned this. So this was so the story about this Ahmet Shabana and Jussi Sopanen. Did I explain that to you already?
No, not that one.
Okay, so then after I think that I finished my first year in Chicago and I started my second year in Chicago, and then there was one guy contacted me from Finland. He was Jussi Sopanen. And Jussi Sopanen wanted to make a visit to Chicago, 3 months visit. And then of course, the decision was made by Ahmet Shabana, yes, you can come. go ahead and work with us. Now this is, by the way, the usual story that you're building your network. So you want to get to know somebody, you go and work with this person. And this is the way to increase your knowledge and to get your better network and so on and so forth. Jussi was following this idea. Okay, Jussi came and he got the simplest possible assignment. And the assignment was, to verify this whole story, what we've been discussing so far, against the commercial finance element software. Could it be easier than that? Okay, so Jussi started his work, and then after a couple weeks, there was a meeting, and in the meeting, Jussi came in a meeting and said, I cannot do it. And I was like, oh my God, this is embarrassing. This guy is in Finland like I am too, and now he's gonna kill my reputation too, not just his reputation, because what's wrong with the guy? Simple assignment. Can he just do it? Do it. And it's simple like that. And Jussi was, I'm still not finished, so I need more time. Okay, then there was a meeting after a month. Jussi came again, I cannot do it. And I said, okay, this is getting to be like too much to deal with. So how long this gonna take? Another month after 2 meetings, Jussi came again, I cannot do it. Final meeting after 3 months, I cannot do it. And everyone was happy to send Jussi back home because he was no good. No good. So he couldn't make it. Okay, then it was much after that, I finally came back to Finland. I met Jussi. Jussi said, I know why I was not able to do it. And I was, okay, tell me. Well, maybe I'm not even willing to listen because this is still so embarrassing. But tell me what's the reason? The reason is that this new method is having a problem. So it is computing things incorrectly. Wait, what? Seriously? It's that possible? Yes, it is possible. There is something that the method is suffering from, which is very common in the finance element community, and it's called locking. Almost all finance element suffers from the locking. And there are many different remedies, many different ways you can fix the problem. But if you don't fix it, you get incorrect solutions. And Jussi figured out that this method was suffering from the locking. And then there was a paper that was published, this one, 2003. And if you look at my publication, this is not the highest cited paper, but one of the highest cited papers. What is it we learn from this? Think about the pressure in Jussi. Jussi came, going to some place remote, and the people are like, do it, just do it, can you just do it? There is a high temptation that you kind of figure in mixing the parameters and numbers to making them look good. But Jussi was not willing to make a compromise. But instead he said, I cannot do it because the solution is not correct. And he figured out why it is not correct. This is a very, very important story. Because usually, average doctoral student would say, okay, let me fix it. Let me twist these numbers somehow that you can get something that looks okay. The case that is okay. Jussi was not willing to do that compromise. Think about it. Think about the pressure. Think about how uncomfortable his life was in Chicago. Very uncomfortable. Okay, so that's the story. So what was this method was suffering? Locking. And he was the one that figured that out. Yes, there is a problem. There is a problem. And the problem is pretty severe. And it looked like, here you can see that, you're slowly converting the right solution, but it takes thousands of elements to do the correct solution. And this is a typical case of locking. And it happened. So there was a lot of activities in the community to fix the locking and, what the ways to do it. There are different variations that came along. This is what, if you know this Professor Marko Matikainen, he's very much specialized to higher and lower order elements, particularly these higher order elements, meaning that more partial differentiation, these are the ways. And then there's Kimmo Kekkonen. This guy, he's a teacher in a bachelor level. He was the one that was looking at these lower order elements. So many different kind of variations. Okay, so these are then the cases. So one of the special verification case. This is not really an important industrial application, but this is a verification where this element was tested. There are a number of verification tested, by the way. benchmark test. This is how they are called, to figure out are they behaving correctly or incorrectly. This is a very, very typical case that you develop the new formulation, you put your formulation under this benchmark test. You see how is the computational efficiency, how is the accuracy, and so on and so forth. One of the cases is this flying spaghetti. So you take a spaghetti material that is close to spaghetti. You make this spaghetti to fly. Sorry that the view is a little bit flat. It should come, there it comes, and it flies like that. This is simple thing, very difficult to compute. Very, very challenging to compute. Okay, some other, these are no longer benchmark testing, but just an example of what you can do with this element, this formulation. Belt and pulleys, like we discussed earlier. Then this is from the Xerox machine, so how it behaves in a Xerox machine. Then the cable dynamics. This is, by the way, still a very hot topic. The cables are something that are heavily used also in a real-time simulation because of the different kind of cranes. And amazingly, many cranes are still using cables one way or another. And then it is a matter like how efficiently you can compute the cables. And can you take all these phenomena into account? So cable dynamics. Then the catenary system, the pentacatenary system, this is the one that you can see in the trains. So this is where the electricity is transferred to trains. This is the one other example where this kind of formulation can be used. Then these leaf springs. The leaf springs are kind of special. They are not so easy to compute because that's a typical example about the nonlinear deformation. Nonlinear deformation because it's like this one here. So the leaf springs are having some bending, so they're initially bended. And then there is a, let's say that this one, take it out here. So there is a joint here, and there is a simply supported beam condition here. And then there are press here. This is where the wheel is connected. And when the force is pushing this leaf spring upwards, this end is here moving left and right. This is exactly the same case. Remember about this cantilever beam. And you loaded the cantilever beam, and you look like where this end of the cantilever beam is going. Is it staying in the loading line or not? This is the same kind of problem. So to be able to analyze this, you have to use nonlinear strain displacement relationship. And leaf springs are still heavily used in vehicle applications. Not necessarily in the passenger cars, particularly not in Europe, but in heavy trucks, they are still in use. Okay, these are the papers. You can see the papers that you can get more information. Then the biomechanical application is like own family of papers. This is something that is also heavily studied here in LUT University. And the one application that is particularly in our interest is Achilles tendon. The Achilles tendon, that is the one that is here. The Achilles tendon consists of like three beams that are connected together. They're very close to each other, and the behavior, to be able to analyze the behavior, you have to be able to take these three beams into account. Very complicated things. All the biomechanics is a nasty business because the material is so complicated and the behavior is so non-linear, so the biomechanics is not easy field, not at all. Okay, so that's the one application. Then different kind of like nano-electronic mechanical systems, and the pipe conveying fluid, the fluid is going inside of the pipe, how that is behaving in the case like that. The optimization is one more example. And then something that is very much in a fashion at the moment. And this is where my in-class quiz, the only one today, is related. You guys are ready? Okay. So this new area is related to isogeometric analysis. It's like something that is initiated from the finite element community. An isogeometric analysis is something that instead of using this, well, the shape functions are no longer here, but the shape functions that are based on polynomials, remember this x power 2, x power 3, and so on and so forth, you are not using polynomials, but you're using NURBS. What are these NURBS? Well, they are non-uniform rational B-splines. So they're like more complicated drawing objects that are heavily used in CAD software because the polynomials are limited. So they're limited in a sense that you cannot even make a circular shape, correct circular shape by using polynomials. But using NURBS, you can make it happen. Now, the problem in finite element community is the fact that most of the models are initially based on CAD drawings. So this is the way that you're building the finite element models, that you take a CAD drawing of something, some kind of a body or a system that you wanted to analyze, and you take the geometry from the CAD, you put the CAD to finite element software, and you do the meshing. Now the meshing is difficult because things are not kind of communicating, because in CAD software, everything is described by NURBS, whereas in a finite element, there are polynomials. And this is causing this mismatching. And this difficulty that when you do you generate the meshing automatically, there are certain things that are not well described. There are certain geometries that are not well described. So then you need to redo the drawing in a CAD. You need to do the meshing again. And this back and forth takes most of the time. Analysis itself is like that. That's not a problem. But building the model, that takes quite a bit of time. Now there's an idea. Why not? Or just use directly the NURBS. Use the NURBS in a way that these finite elements are based on the NURBS, not polynomials. So then you don't have to fight between this mismatching. And that's what the isogeometric analysis is about. So using non-uniform rational B-splines, that's what it is. Okay, how that sounds? The problem here is that then you're kind of losing a little bit about physical interpretation, but then the meshing, which is a typical problem in today's finite element modeling, that's solved, completely solved. Makes sense. So are you guys using have you guys used the real serious finite element modeling? And typically is such that you're meshing everything by using solids. That's the typical scenario. Regardless how is your structure, always solids. And sometimes you end up to have a lot of elements. Sometimes you're missing some of the geometries. Sometimes there could be a hole that is where the bolt is going through the structure. Then there's an awful lot of elements in that detail. Okay, but my question, it's not coming yet. This is a conclusion, so it's coming momentarily. So the conclusion was this vectorization procedure. This was a key element in the Absorb-Noddack-O'Neill formulation. These are the application: vehicle dynamics, biomechanics, rotating structures, optimization, multiphysics, cables. Here it is. In isogeometric analysis, finite elements are based on NURBS, finite elements are based on polynomials, finite elements are based on trigonometric functions, finite elements are based on imaginary functions. So which one is correct? Okay, so let me take myself to, sorry, not this one. Still seems to be 0 answers. Are you guys still logging in or? Okay. Okay. So the first one is here. Second and so on. So what we have here, 6. How many participants there is in the YouTube?
5.
5. Okay.
And I believe that at least half of them are us.
Ah, okay. I see. Is it because of this student party that is mixing things?
No, not at least for us, because like,
They're
you know,
just studying at something.
mechanical engineering students can't have fun.
Really?
Yeah.
Yeah.
So who is the ones that are there in a parking slot?
Business.
Business?
Students, yeah, they don't have nothing to take care of.
Bachelor's.
Mass. So they are what?
Even
Bachelor.
master students, like
Bachelor's student.
Bachelor.
even master students.
Most of them are there.
Yeah.
Yeah.
But
Are you
based on
guys
that,
sorry
no,
because of this?
uh,
Because we make you the work like your ass off.
Because they think that we will have a long journey, about 5 years here, so we have to have these kinds of hard days.
Actually, like, I don't believe that this kind of thing is possible even for, you know, mechanical engineering bachelor levels, because like we have this course that we are in charge of some, like mechanical engineering students in bachelor levels, you know, as managers and everything. And when I asked them about that, whether you can participate in any events or anything, they say no, we can't. We don't have enough time.
Okay.
But for business students, it's still like they have, like, yeah, as much as they like.
So is this a problem then?
Yeah.
So it is a problem.
Yeah.
Okay. 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 So I got 11 answers. So okay. Let's see.
100%?
This is gonna be 100%.
Yeah.
So, but no dancing. Why?
not?
Because the threshold is 20.
You know, you always come up with some kind of excuse.
Well, you know, I always been saying. I think that I'm consistent here. I always say 15 or what is my threshold? Don't remember.
And you know, the last time that we could get 100 somehow, you sabotaged it.
No, it never be. It's
There
never
is
be.
right.
Okay,
Obviously.
someone else.
Yeah.
No, there's Okay, let's take a look. Here you go. Here you go.
Oh.
So they are based on polynomials if we use speaking about the conventional finite sum method, but not about the isotrometric. Yep. Okay. Back here. All right. Midterm exam. Yesterday, I really worked hard to figure out when is a midterm exam. Couldn't find it. Honestly, I couldn't find it. I look at all the places. I look at from there's uni.lut.fi. I look at from the SISU. I don't know. When is the next midterm exam? Where are you gonna check that?
Model.
Moodle. No, you can't find it in the Moodle. So where you can find it?
Exactly exam time. When you can find
Where you can find the exam time?
Isn't it the final term exam?
That's a different. Okay, so that. Hey guys, so there are two different exams. So which one you?
elut.lut.fi. You can check.
What?
So can you find anything related to that?
What was it? lut.lut.
elut.lut.
It's for example.
No.
This one. So can you guys see? Is it correct?
Yes.
Okay, and then what? Let me switch this to English. What's the next thing to do? Okay, so where did you find that? So you went.
This is the
Okay, let me. Okay, I think it is here then. Student life. So did you select this study guidance as support service? No.
Actually, I was just this link. I don't know what is the previous state, but you can check from my laptop.
Okay. But when is the next midterm exam?
About the paper or model exam, yes. Exam by.
Let me try to find it here.
Yeah, they have.
Events. Huh. Okay, I think it is just have to be here. Oh, this is a completely new website. I haven't been here before.
Yes.
Okay, so the question is, when is the next midterm exam?
There is no meter exam for simulation.
Really?
Yeah, at least is there a final?
So there is no midterm
Yeah,
exam
final.
because
Final.
Yes, information.
you were referring this full exam. Full exam is, I think that it was May something. I don't remember exactly the day. Maybe 10th. So that's going to be the paper exam, which I don't recommend you to participate. But go to this midterm exam.
Yeah.
But when it's going to be? When it will be? Or is it something that we can make that decision by ourselves? Honestly, I have no idea how it goes. Because it used to be something that was selected by Student Affairs Office. Like they selecting the lecture time and the place. There I have no power to affect to that. And that's why it is Monday morning at 8 o'clock. You know, no one would like to have a lecture that time. And I think that they really hate me big time because this is not my first time to have a lecture Monday at 8 o'clock. I don't know what I made wrong. Honestly, I don't know. Okay, but can you find it out?
I found it for the paper exam.
Yeah, but that's that's a May 10th, isn't it? When is the paper exam?
10 of May.
10,
10th of
May 10th.
Yes.
Okay, but what about the midterm exam? Because we need to learn when is the next midterm exam.
Oh, I couldn't.
And by the way, don't you have any authority to change it like the way that it was last semester? Because when it's fixed on like some particular time, it's some kind of
That's going to be hard because we don't have a question bank for this course.
oh.
So it's not so easy. Well, we kind of have, but because all the questions you know in advance. You know it in advance, but there are quite a bit of differences. What is the level of difficulties in these different questions? That's why it's not fair if we use a lottery to select what question goes to you.
Completely understandable.
But so then we need to make a decision when we're going to organize a midterm exam. Any proposals?
First week
Instead
of
of
May.
No,
First week of May.
Okay. So that would be fine.
Okay, it's first.
May 7th.
Yeah.
No.
Okay, so next week is so the last lecture could be 25th. Okay, what about if we're gonna have already on that week, like the last week of April? Last week of April.
Somehow it's buried under many assignments on that week.
Okay, so that's a good idea.
The deadline of everything is like the
Okay,
last
I
week of
understand.
April.
I understand. Okay.
Let's change our procedure.
Okay, then the next opportunity. You said first week of May. What about Friday? Is that not a good idea or Thursday? Or is it Thursday better?
Friday is good.
Friday is okay. What time? Okay, let's go back to this one.
Afternoon.
Friday.
Uh, because I need to make a notes to myself. Otherwise, for sure I'm not going to remember this. Midterm exam. So what day you proposed? 6th of at what time?
How about 10th of May?
No,
No?
no,
That's Tuesday.
It's okay.
no.
6th is okay.
Yeah.
It can be on weekend too. No, I think it is. I think that's illegal. Yeah, I think it is illegal. No, it's illegal. It for sure is illegal because, you know, just a couple of minutes back, you guys were complaining that you don't have enough time to drink and they have a
We
party.
don't have any problem by
But
that.
now if we're gonna have an exam in a weekend,
Just one weekend.
no.
It's
I think I'm gonna be in a trouble because they're gonna make a story of me like I'm a really a nasty person forcing the students to work in the weekend too. Okay, so 6th. So what time would be good?
4 p.m.
Are you guys okay with that?
It can be open for example,
No,
for
no, it's you
4
just
hours.
no, it's just
Okay.
that you can't be.
Okay, what about at 1 o'clock? 1 p.m.
No, like
Well-
if it will be like the midterm, it was I believe it was from 4 to 7.
Yeah.
Yeah,
But Friday 4 to 7, is that okay
it's
to you?
okay for us. Like even Saturday or Sunday. We
Okay, let's what about this compromise? 2 o'clock. At 2
Yeah.
o'clock.
But no, I believe that like having more of the time on your hand because like
Yeah, this
still
I mean that this
studying
is
about-
getting started, we can make up plenty of time for the
How
exam.
about morning?
Not
Morning is good too. So 6 o'clock. Is 6 so what about 6 o'clock? Is that too early to you?
I rather I rather be on the afternoon because if it will be on the morning, I believe that I will
So
not be able to sleep.
you're not gonna score well.
No, I will not be able to sleep because
Okay, because you're thinking all the time.
Yeah.
Okay. All right. So at 2, I will let you know about how the details gonna go. All right. All right. So here are the things that will be asked, and the same story than the last time. And I can organize this voting if you want. Voting that you can select the question that for sure will be in exam paper, and the question that for sure will not be in an exam paper. Okay. All right. Okay. So these are the stuff. So the content modeling. So this is not in the right order because the first ones are visiting lectures. And then the content modeling, stress analysis, multi-body system dynamics in fatigue, blast deformation, and they are again rated by star. Now the visiting lectures are emphasized this time, as is the content modeling. Rest, not so important. So, and again, look at the questions, make sure that you can answer each one of the questions, and that's how it goes. Biomechanics. And like I said, I made this mistake in a biomechanical lecture. Hold on. So, I think at this one. No, not this one. Why is this now looking so weird? I think it is this reading mode. Okay, so the mistake that I made in the biomechanics was that I did not click this go live in YouTube Studio, and because I did not click it, I don't know where the streaming went. So there was a streaming all the time on, but where is located? No one knows. No one knows. I thought that it's going to be automatically somewhere in our YouTube channel, but I'm unable to find it. I don't find it. So what I did was that I created a playlist which says Lectures 2022. And if you look at this playlist, all the recordings are from this year, except the biomechanics is from last year. So that's the way to see how was a biomechanic. So there was quite a bit of 5 questions in biomechanics. So I would say that, let me see, something that would be that I would kind of like to emphasize out of the many questions here is like the question number 1. So maybe I should put this in a ball. This is the one that I would like you to take a look. This one. Oh, now I'm not fitting it well too. Here, this one, and the second one is this one.
And by the way, I feel like you haven't uploaded any just you have uploaded just 2 lectures for the
Yep, that's right, that's right. So I'm gonna do that as well. So, but what I did very recently was that I was editing the YouTube videos. Well, I cannot say really heavy editing because what I do is that I will take the beginning off. Just cutting the beginning because in the beginning there's usually quite a bit of things that are not productive and like setting things up and that kind of stuff. So I took that away from each of the lectures. But other than that, not so much. Okay, so these are the biomechanical questions again. How to prepare yourself to midterm exam is make a team. Ask your friends to get together someplace. Practice the way that each one of you can answer these questions. So that's the way it goes. And you can even, go ahead.
For these 2 questions are regarding referring to all of them.
They're all of them, but these are the one that I wanted to emphasize because there are 5 questions. So make sure that at least these 2 you can answer. So make a team, divide the task. Such that, one will figure out how to answer the first question, second and so on and so forth. And then you make a study group. And the study group will be the easiest because some of the questions, you really need to look at these videos carefully to figure them out. And I think this kind of team learning is heavily emphasized here. I see that you guys are teaming up anyway, so you have a lunch and everything together all the time. So
like I believe that's last time we were studying till I don't know when together.
Yeah.
so you make that as a team effort.
And somehow like we have set it in a way that we have everything together.
Yeah, makes sense. All right. So that's my advice. This is just a screenshot from Adam's lecture. Remember that the biomechanics and the mechanics, it's kind of same story. So they're not so much different because human joints, even though that they are not really revolute joint, like a knee is not the revolute joint, more complicated than the knee, but typically is modeled as a revolute joint because the way the knee is moving is like there is a translation and rotation. So it's a bit more complicated. In some special cases, but special cases only, this translation is taken into account, but usually not counted. Then the bones, which can be flexible, but usually they are not flexible, is sent at the bottom. All right? They're connected together by their joints. Muscles are forces. They are forces. One of the important things to understand in the biomechanics is because the control of biomechanical system, knee, is very complicated. And it's not possible to see I'm going to ask each of the muscles to do something and then somehow I'm able to synchronize it. That's not going to work out. Think about how long it takes for a baby to learn the walk. It takes a year to learn the walk. And this is that you need to make sure that the wiring between the head and the muscles are in a certain level. And then this walking is beginning like this. So it's very, very complicated. To make these biomechanical models to move and do something, always, one way or another, based on the measurements. One way or another. Typical ways that they are based on the measurements is camera technology. So you're making a video out of the human motion. And then there are these trackers that based on the video images, you're figuring out the tracker tracks curves in 3-dimensional space. Or you can use accelerometers, IMUs to figure out the same thing. And once you have this path in space, then you're making your model to replicate the motion. Once the model is replicating the motion, then you can see how is that the muscles are behaving in that motion. Are they extracting? Are they constructing? And this is the way you can start optimizing the force production based on the muscles.
Can you even measure the tiny flexibility?
You can measure the tiny flexibility from bones, in certain bones, but only need to be bones that are very close to surface. And there are only 2 locations in a human, 3 locations. Here, where is it? There's one bone that is fairly close to surface. And then tibia, here. This is close to surface. But of course, the measuring the deformation from the bones Oh my God, this is really, really nasty business. And what they do, what the Adam was explaining, was using this in vivo testing. In vivo, it's you guys know what that is. Vivo, in vivo. You take a dead bodies. You take a piece of dead bodies. You make these piece of dead bodies to walk. Yeah, I know. But that's what this is how they're analyzing the knee joint loading as well. You take a dead body, got it here and here, you put it in robotic systems, and then you can easily put kind of sensors here. But living, that's not possible. I mean, except that prosthesis, some people have a prosthesis, and then maybe you can add some sensors to prosthesis. But typically that's very difficult. So that's why there's so much testing that is carried out for dead people. You guys didn't show that the picture that Adam was showing, it is a piece of human body. For sure, because you saw the piece of human body, that body for sure is not alive.
Should it be fresh? Because like.
Of course, it need to be fresh.
So imagine that like standing on top of somebody's day. Okay, go ahead, die. I want to like cut off a
But think about how you see there's a Frankenstein movie.
Yeah.
In reality, it's worse. In reality, it's not so pleasant. Because well,
yeah.
but that's how it goes. That's how it goes. There was an idea. There was a while ago. There was a thinking. We were thinking that should we somehow try to do some testing here too. But these people, these places where they do this testing, they said that it's so unpleasant that you don't believe it, and I can believe it. So it's not pleasant then. So these strains, you can get it from the human. You can get it from only from certain region. And typically, this region is not very interesting, but this area is hip region. Think about how deep below the muscles your bones are located. There is no way that you can measure it. Other way that there is a. Okay, so that's what the biomechanics. So, but so much about because it's so unpleasant to get these measurements from the real cases. That's why the simulation is nice. It's nice. So you can just do this, get the motion, and once you get the motion, then you replicate the motion by using the simulation model. And when you do that, that's when the muscles are learning. That's how I should behave. There are also these sensors that are measuring your muscle activities. You can use those as well, but still this optimization and teaching is very, very critical. Important. Okay. Take a look at the Adam's slides and you can see something. Maybe he was, for sake of courtesy, he didn't show those figures. Okay. All right, PLM, difficult. This was difficult. These are the questions that I got from you.
I believe that this is our second time.
Yeah, this is very, very hard.
Those two general.
They are. They are very difficult. But again, use your power and walk one of these off. So then there's only one that you need to focus on.
Yeah.
Maybe this is the easiest way to go.
The
But-
problem is like, we've had this course of IPSS.
Oh, you guys are in this course.
Yeah.
Oh, that's why. Okay. Now I'm late to learn. How is this course?
Amazing.
Okay, amazing in a positive or negative way.
I like it.
Okay. So you hate it and you love it?
But let me explain. Like, the course is fine, but I believe that it's first of all, like we've had several course members that they were not from mechanical engineering.
Of course, because it's designed for industrial engineering.
Yeah.
More like a business.
Yeah. Industrial engineering here is close to business.
Yeah, I like the business part of it.
Really?
The course is too general. Like, you know, all of those stuff, like they were so general, and I'm like, we were on the same group, in the same group for the course, and we just talked about a few stuff related to mechanical engineering, and they said that your stuff are so practical, and so like, it's
Yeah,
not-
I know, but I think that I got an idea what you guys are saying because we also have this more SIM platform, this research platform, where I'm cooperating with people from business and people from industrial engineering. We had a meeting last week, Wednesday, and in the meeting, there was a discussion a little bit about the teaching, and then they, I complained that you guys, when you are answering the questions or making a papers, you're telling too much. You're just making things too complicated and too lengthy. Because in a mechanical engineering, the most important thing is to focus. Second most important thing is focus, and the third one is focus. So focus and write only the thing that is asked. I don't write about how was my summer vacation and how is the weather today. I don't care about that. And this is exactly the style in industrial engineering. This is of course extreme case, but they even when I'm teaching my doctoral students, there are a few words that are not allowed to use. Don't use like very. Don't use quite. These are the words that are telling nothing. There are many. The list is kind of lengthy. And I mentioned that these are the words that are not allowed in a mechanical engineering. They were, what? These are the words that are encouraged to be used in an industrial engineering.
Yeah, it was completely like different from what we have in mechanical engineering.
I know. And they say that it's so important to elaborate, so important to tell something that is kind of related to subject matter. And I said that in mechanical engineering, you will be penalized because of that. You will get definitely penalty if you're telling too lengthy.
Especially if you're, the one who judges, like Harry, Professor Harry. Like, if you bring one of those words very high, so why?
Okay, what is this? What is this?
It's high compared to what?
Yeah.
Like,
Quite what? Quite what? So that's a gangster rap language.
yeah. So it was completely different because of, as you said, all those lengthy things. Like it was something new, but the idea and the topic, it was something interesting. Like all the things related to PLM and everything. It was something new, but as you said, lengthy.
Okay, I got it.
Actually, I don't think so about it like this. I agree with him about the method of teaching them and the response which have to give to them. But I like our topic, the implementation of IoT machine. And we did it together. I always think to improve how we can improve, for example, the machine system, for example, like CNC or I don't know. And nowadays the only way to improve everything is implementation of IoT.
Okay, I hear you, but I understand you completely. But I understand you others too, because I feel the same pain. Because
Yes, this part is boring, I
Yeah.
agree, but this other part we learn and we understand what's IoT here.
Yeah, that's-
study.
makes sense. But I know that because there've been short period of time, like almost like flashes, that I feel that okay, now I understand these people from industrial engineering, and the next sentence again makes no sense, and I'm like, oh my god, I'm never gonna learn this. So this is something.
As our topic, like implementation of IoT in like machining and everything, stuff related to technical stuff, how to implement that. So what would be the benefits and everything related to that, they were super fun. They were super interesting. But stuff related to those kind of lengthy like explanation and everything.
Yeah, I know. Okay, let's move on. So here is a question, two questions from bicycle dynamics. I think that this is quite easy. There are short answers needed. Lengthy questions, but short answers. Okay, let me move on. Contact modeling. Four questions. Explain the concept of bounding box. conduct description based on penalty forces, advantages, disadvantages of penalty force. What is a many body dynamics? Many body was these inequalities and a lot of bodies, thousands of bodies. Those were the things. This is this bounding box that you go from bigger object to smaller. That's the way to go. Penalty forces and complementary, those were the two things. Stress analysis in multi-body dynamics, how stress history can be evaluated using multi-body system dynamics. And this was these two methods. So you can use these model matrices, or you can send your forces to finite element method and compute the deformation. This has this nice name, linear theory of elastodynamics. This is more now, this makes more sense, way more sense. Okay, then multi-body dynamics in fatigue. Why welded structures are vulnerable for fatigue damage? Remember two cases, two reasons. Have you, by the way, participated in the course which is like fatigue something? So you were in a fatigue course.
I will in the course in next semester.
Oh, it's in the next semester.
It is in the SSRG package.
Okay, okay, so it's gonna be in fall. This year fall.
Yes.
Okay, I got it. Others, you're not planning to participate in the fatigue.
Like
Our major
I
is-
mean, you know, as a, some kind of, what is it called when you take something out of your,
It's optional.
yeah, something optional, because like it seems fascinating.
Okay, okay, so it's a
Elective.
But we have some session about the fatigue in SSRG 2 course.
okay, good, good. So you're aware of this problem associated to welded structures.
Yes.
Good. Two problems.
About the stress concentration.
Yeah, two problems. Initial crack, and the second problem is a high residual stresses. Then this local geometries is a problem, also a little bit problem, because those will increase the stresses imposed to the crack. So three problems, kind of, but two major ones. Initial crack is a big, big problem. If you would get rid of that, that would be great, but you just cannot. And then the high residual stresses, that's hard to get rid of. Really, really hard to get rid of. And that's why the high strength steels are not helping you so much. And then the stress concentrations, that's another third problem.
Some post-processing can be.
They can help. The problem is that there's usually, because of the cost, you want to make your product to be as affordable as possible. Welding is typically used because it's a very affordable joining technique. But it becomes to be expensive if you need to look at carefully, and if you need to use this post-welding treatment. So then increase the price. So maybe it would be better just live with a crack. That's what they do. That's usually what is being made.
But it's related somehow about the safety. Where you want to use this structure? For example, in the bridge or in the.
Sure, but still it can be monitored. So people usually prefer to monitor and live with the crack because there's this is statistical thing. So it's something that you can control and you can monitor how is a crack growing. By the way, one of the easy way to reduce or increase the fatigue life is that use a really overloading every now and then. Overloading is a simple trick to do it. That improves fatigue life. Yes, it sounds like really, but yes, it helps. Why? Because what happens when you do the serious overloading is that there becomes to be a plastic zone in a place where the crack is growing. So there's going to be like a really severe plastic zone. And the crack have to find a detour to go around that plastic zone. Yeah. So is there, where is it now? In a crane. I don't know if they really use it in a crane, but sounds like a kind of wrong way to go, but this is the one possibility. So if you have like just a cantilever beam, and there's a crack growing here. Now you're loading that heavily. So there's going to be plastic, now this is too small, but like plastic region. Let me make this bigger. So the crack is growing here. This is this structure. The overloading, there's going to be plastic zone here. Now the crack have to go like this, and then it grow again. Don't try this home. So if you have a problem in your car, the answer may not be to try faster, because this means overloading, serious overloading. Okay. And this is the way that you can do this fatigue analysis. You can get stress history. You use this rainfall analysis. You convert that to be equal in stress loading, and then you can do the fatigue analysis using these methods. Lots deformation cases. Okay, when transverse shear plays an important role, when there's a thick structure, simple like that. Isogeometric analysis, that's based on the nerves, and then kinematics used in the absolute non-Arconia formulation. So it's this based on this vectorization. Okay, now, and this was the absolute non-Arconia formulation. This is a master thesis. Okay, I don't think we have a time to do it, but I would like to discuss about subject matter like this. How to select the topic. Can you change the topic? These are the things that I would like you to be aware of. Are you aware of this kind of stuff? So you are. Was there a lecture that was delivered about the thesis work, or how you know about that? Okay, you can get the topic from a professor, from a company, own contacts, mailing to companies. Check this one. This is something we discuss in a career counseling. This is one opportunity to find the thesis position. And then it's still a good idea to contact whoever is your professor. All of them. So if you have multiple professors, contact all of them. And then ask like if there's a topic available, if there's a contact available, what kind of topic is okay.
And at what time? When you're nearing like the last semester of?
Like you should contact pretty much this time, because you're finishing your first year.
Yes.
And you're gonna get started in your thesis work in the next academic year. So this will be a good time. This is a good time. It's good to mention like what are the topics you're interested in, what are the strengths and weaknesses, this kind of stuff. Industry is good in the sense that it helps you to get the position afterwards. That's the major advantage. Salary, maybe the salary. University, okay, support from a professor. Again, I heard that this varies a lot, so it's not necessarily the case. And also you could get the support from a professor even if you work in industry. So that doesn't make that much of a difference. But the location, this used to be important prior to this COVID. Now everything is online, so even this is not so important anymore. But location, possibility to carry out the courses, exams, certain help. Yes.
Can I ask a question?
So of course.
Does this related to our CVs to reach a position for our thesis project in industry or university?
Is it making a difference in terms of your career possibilities? That's what you're asking.
Yes, I mean that. Does it important what is our CV or no? I mean before experience in industry or.
Could help. It could help a little bit, yes. But basically, each of you are eligible. For sure, you can get the position anywhere you want. Your master level students, that's all that is needed. So
because there is some difference between some students, for example, me in my case, I'm 24 or 5.
you mean the age? Yeah, I don't know. I don't.
didn't have any experience in industry real.
Yeah, I don't think I think they want to see a good person. They want to see a good attitude. And if you go there and they say these magic words, which is can-do attitude, that helps. That helps. Okay, so let's see how much we can go over these topics. Commitment. It's good to know like what is the role of their work in industry, why it is needed, what are the responsibilities? All the responsibilities. Because sometimes they hire you to do sales work. And your thesis is like a side business that you can do your thesis every other Friday or something like that. That's going to make your life difficult, but that's one possibility. It's possible to do it this way. If there is a salary, and think about how is this make sense to you to do, how it makes you stronger. Okay, your case it will be clear, so you can get the experience from industry. So it's a good story. Now, do you have the knowledge to do the work? So if they're asking something like really specialist in a finite element, you have never used a finite element method, maybe you shouldn't take the topic. Those are the things that is good to think. And note that you can select it this just once, not the multiple times. There is this misunderstanding that you can pick the one, get started, and if you like it, leave it. That's not going to work like that. So this is going to be your topic, and the topic itself doesn't really define your grade. There is a myth that you take a position in university under supervision of the professor, you're going to score 5 automatically. And you take a position from industry, max 3. It's not like that. It's not like that. Okay, salary. This is I think we should close soon. Let me try to explain as much as I can. Scholarship. This scholarship salary, this is related to financial support. Scholarship. There is a support foundation that you can organize your financial support through this support foundation. How this works? This works in such a way that the company that you're going to do your thesis work will make a donation to support foundation. So they're going to make a donation. And then they're gonna open a call, and they're gonna select the one candidate to this call. So it goes through this support foundation. It's beneficial in a sense that this is a scholarship. Because it's a scholarship, there's no taxes. Taxes, they are highly progressive and highly case dependent in Finland. So it's hard to tell what is your tax percentage. But this is the tax free. Salary from the company, salary from the university, no salary. No salary makes sense too, because this is investment to you. This is mostly investment to you. But this is sometimes that I can see that, if are you a member of this tech union? I don't know where this tech is. Tech is like technology union. It's a union. Are you a member of the union? Most of the cases, the students are a member of the union. Have you heard this tech?
Yes.
This one. So let me show the website to you. I don't know, maybe you are not.
Yes, we are.
You are a member of this.
Yeah.
Okay. So this is a union. So you guys are union activists. A union, well, you're a union member. So this is a union. So the union, if you take a look at the union, what the union says about salary recommendations. Let's take a look in English. How can I find it? Salary. Okay, 104. Recommendations. Here, salary recommendations. Salary recommendations. Okay, this is a salary recommendation that is mentioned by your union. So these are the points. This is a salary that they're expecting you to get when you are a thesis worker. And this could be a little bit of problem because this salary is somewhat high, and maybe if you get started your negotiation before you even say your name, you say hey, my salary requirements is 2,820. This could make your life difficult. And think about that. This is for and mostly the investment to your future. I like mentioned, to get the position in industry helps you to in a longer perspective to do good. Okay, so this is this is a recommendation. Yeah, this is a recommendation for master thesis work. Be ready to compromise this. This is my recommendation. Okay. Nature of the work. 6 months. Let me walk this through fast. So 6 months independent work, demonstrate your maturity. That's what it is about. Demonstrate your ability to solve the life's problems. There are midterm discussions where that your supervisor would like to see how your work is developing. The instructions to carry out the work. Make a table of content of your work. Research plan. It works as a research plan as well. It can be used as a timetable as well. Organize a kickoff meeting. Make a high quality literature review in the beginning. Start preparing a manuscript in the beginning. That's extremely important. Let me see. Reporting. Make sure you're following or using these 5 chapters. That's the way to go. Always 5 chapters. So, introduction, where the most important part of the introduction is the objective of your thesis work. And then once you're in a conclusion, you're explaining how it happened, were you able to accomplish those objectives or not. Look at that. How come he's doing, why is doing something like this? What number is it? What number it was? Was it? This is not the perfect number, but that's okay because we are about to close. Conclusions. Here are some final tips to you.
Like, is it possible to go through it in more vivid detail?
Sure, I can do that in 2 weeks. I can do it in 2 weeks.
Because somehow I believe that we are not doing it justice. Because going through it so fast. And
Sure, I can spend more time if you find this useful.
Yeah, sure.
Okay. Like here are the things that I would like to explain. Like, this unspecific statement, quite large. Here it is again. So it's not acceptable. But then there's an uncompromised, like very much like you say, all the machines. I have good stories about this language that is too exact. Because it's hard to find. If you say all machines are this and that. Okay, I'm not going to tell a story about that. No, do not try to be funny. There are no cases that I've been laughing. Sometimes I'm crying because people try to be funny and it's not working like that. So, jokes, they don't work. Okay. All right, but let me get back to this. So it's going to be in 2 weeks. So, and then we can, I can explain a little bit about this kickoff meeting, like what is the purpose of the kickoff meeting and this kind of stuff. And then we can take a look at this reporting. This reporting is important because you find the style, you're always following the same style and you do good.